All right, so in next topic, I'm going to spend about 15, 20 minutes to talk about how to make a cable antenna measurement, why it's important. All right, recently I walked into a site, I talked to one of the technicians. So one of the issues is I say, okay, how to make an antenna? He's maintaining a radar antenna. And he said, oh, okay, I make a measurement, I do a return loss. But one issue I have is every time, the first day I make a measurement, a month later I make the same measurement, the measurement results are different. Why? So basically in this paper, we're going to show you how to make an accurate measurement and why antenna and cable measurement are important. Antenna is the only pipe between wireless system to over the air. So in this show floor, there are many antenna manufacturers, designers, simulation software. All it does is try to simulate, will help you to design a good wireless pipe, I call virtual pipe, between the backhaul towards the end user. And whether it's good or not, that will really depends how people manufacture, how to install, how to test it. And today, in this paper, we're going to more focus on the testing. So typically, we see antenna, we see is typical, in the industry, we call line sweep, or distance to fault measurement. And actually, there are a whole bunch of measurement and the line sweep. You have a return loss, distance to fault, and the cable loss measurement. That's what we're going to discuss today. And really look at the cable as well as antenna two portion. First of all, let's look at cable loss measurement. Cable loss is actually really critical measurement, especially you go to higher frequency, because we all know the higher the frequency, your cable loss tends to getting bigger. Especially if you have a broadband signal like a radar or EW signal, you cover such a wider range. For example, the radar on the airplane, you have a pretty wide frequency range. And depends on what type of cable you use, there's a pretty big loss. There's three types of measurement you can do to make a cable measurement. First is we do a measurement for single port measurement, typical for longer cable, but a relatively low loss, like a cell tower or a waveguide for the microwave backhauls. And we also can measure the long cable on the airplane. So there are really three methods. One is a two-port measurement, typically for shorter cable. You can do a S21 measurement or insertion loss, depends on the industry you happen to be. And if you have a pretty long cable and on the tower, it's not realistic to make a two-port measurement, we all know that. So in those cases, we use a single port measurement. Essentially, you leave the other end of the cable open or short. So just force the signal reflect back, so the signal will travel the cable by twice, and then you can make a measurement. And we'll compare both two-port and single port, see which one is the better one to use. If you happen in the very long cable or a huge loss device, you want to make those measurements like on the airplane or radar. And you can use a power sensor to make those measurements, because when you make a power sensor USB measurement, the frequency on the USB is much lower, so you don't suffer a big loss. So this is a comparison from two-port and one-port. Typically, two-port measurement is a little bit more accurate. There's some special algorithm Agilent developed to help to minimize the inaccuracy created by the one port, because one port you really rely on the reflection. And there's more ripples. You can see this yellow ripple. This is one port, and of course two port is a little bit more better. And we have a special algorithm that actually help you to remove the ripple to get closer to the two-port measurement. We talk about cable measurement. Next step, let's look at antenna measurement. That's another element is very critical. And there are many companies over here, like NSI, a whole bunch of companies, they're doing antenna pattern. And what we do here, I'm not talking about antenna pattern or gain, that's a special equipment needed. Here, really, we talk about Agilent FieldFox really making return loss, distance to fall, or VSWR measurement, how we make those measurements accurate and consistent. Because one of a neuralizer-based measurement, which like cable antenna test, is not, a lot of time it's not about accuracy, it's about consistency, how you make your measurement repeatable. Okay, let's look at the first measurement, antenna oscillation. Why antenna oscillation is important? Now, it's critical for today's industry. Look at real estate on the towers getting very, very limited. So you have a lot of antennas kind of next to each other. And it start interfere with each other, especially when you test antenna, other antenna is hot. So the signal will couple to the antenna and the test. So put a great challenge for test engineer or technician in the field, how to make sure the measurement is accurate. And also in the industry, use a lot of repeater. That's even more critical to have a good oscillation, because if you don't, for example, your repeater 2 antenna requires about 90 dB oscillation. If you less than that, you create a oscillation between 2 antennas. So you bring the whole noise floor up, not just damage your equipment, you can create an interference for the whole system. So that's, we use the insertion loss to make antenna oscillation measurement. So port 1 connect to antenna 1, port 2 connect to antenna 2. And you can simply do a insertion loss measurement, whether you can do a 2-port calibration or just simply do a response cal or normalize. So in this situation, we actually take a 2-panel antenna, 900 meg and 2.4 gig, which is Wi-Fi signal. You look at today, a lot of antennas, they are kind of integrated. You have both cellular frequency as well as Wi-Fi, and that creates a great challenge. So that's easily, we can make those measurements. Okay, just now we all talk about in the frequency domain, we talk about return loss, VSWR, essentially they're the same. And now let's talk about time domain. In the cable antenna industry, we typically not see time domain, we talk about distance to fall, which is a half of the time domain. And how do we create, why it's important? Because now you have, in the early days, you look at, you have a cable, have an antenna, you pretty much can easily figure out which component is the problem. But now you have a duplexer, duplexer, a lot of time you have tower-mounted amplifier. You get many, many components in the system. And the distance to fall become the only way to identify where the problem is. It is different with technology we use over here is different from technology used at TDR in the old days. You send a impulse signal, so you have any impedance change, you see a reflect signal. What we do over here is we call FDR, frequency domain reflectometer. Essentially take a return loss and do an inverse FFT to convert into time domain. Same is easier to do and more sensitive. So because sometimes slightly impedance change, TDR won't be able to detect, but in the frequency domain it's a lot more sensitive because we detect the phase as well. So this is an example of distance to fall measurement. Distance to fall, I see measurement actually is not accurate. Distance to fall is not a measurement, it's actually a mathematical conversion. That's create a lot of problem in the field when you do the measurement. Because since the mathematical measurement, we assume the signal is a periodic signal, so that means it repeats itself. So there are certain parameters you need to educate or let the instrument know. For example, what's your frequency span? What kind of media you're transmit? Because you're no longer in the vacuum, so it will have a velocity factor. And since you transmit on the cable, you're back and forth, so the loss also play a role. So you take all those into consideration. But the nice thing is you look at distance to fall, you can look at each peak. For example, we simulate over here we have a cable, have 3 adapters and the cables. And you actually can read each adapter in each connection what's the return loss is. So this really, really neat feature for we call system sweep. So when you go to any kind of feeder system, including antenna or cable, you can do a quick sweep. You can see roughly tell you what's wrong with the system. Okay, since the measurement is done mathematically, so it depends how you set it up. If you do a distance to fall, you happen to set up a pretty long cable, and there's many reflections, signal reflect back and forth in this situation. So let's see, here is supposed to be end of the cable, or typical we want to see the antenna. Let's see you have a microwave dish or radar antenna. You want to see where is my radar antenna? Here's your radars, or or cell tower for that matter, and if here you get a pretty bad situation, let's say close to open, here we simulate, we leave this open, that means all the energy coming back, and the signal will be bouncing back and forth, then create this kind of like a reflex signal is way beyond your antenna length. So that's you need to need to be careful. This is actually not the signal you're looking for. And of course, you can fix that and just simply connect a load, then this 2 signal will go away. So we look at the cable antenna measurement, we look at the distance to fall. And one of the issue today is we all know the DAS system, or we call distributed antenna system, is getting popular now. Why DAS is popular, you look at the venue over here, have so many vendors, so many people try to use their cell phone or data card. One of the issues is how you provide a good coverage with good capacity and the speed. So you use the indoor system or distributed antenna. You don't want to have to use one antenna just blast everywhere that you get all the reflection. You're not going to get a good service. And so that's people start to use a very low power transmitter inside the building. And of course, you need cables and adapters, splitter to distribute the signal. And distance to fall measurement and the return loss is critical here. It's actually distance to fall measurement is a very neat tool to help you to identify the problem in that system. So this is a demonstration. We basically take 2 couplers and hook up 2 antennas. You can easily see, each one. We can actually simulate whether we'll leave this one open or connected. So this one, if we disconnect, you see the signal is going up. And that's kind of help user to quickly identify which part is a problem. For example, over here, you can easily just see this is the antenna, this is the adapter before, this is the coupler, then the second one, etc. Basically, you got 1, 2, 3, 4, 5. So you can easily, of course, in the real situation, it's much more complicated than that. You just have to test one section at a time. And another challenge is you go to indoor DAS system, typically you have a daplexer, and daplexer is bandpass filter. And you have to really play around, look at your energy, where you want to transmit your signal. If you just blind out, send the signal from DC to whatever the frequency you set, you may see a false signal or ghost signal because the energy all coming back. You're not able to see all those peaks. Okay, so for distance to fall, we said is a mathematic conversion. So there are some tricks you need to do. The best way is we recommend use the low pass mode. Low pass mode basically is all you need to do is tell the instrument, tell FieldFox what's the length of your cable, and our instrument will automatically calculate what's the right frequency for you to use. So give you the best resolution and best maximum range. And in some situation, you may have a filter or bandpass filter in front of your cable. In those situations, you have to use a bandpass mode. So instead of start from DC, you really look at your filters, the start frequency and the stop frequency. and set your frequency span within that filters. There's a problem for doing that. I give you an example. If you are in the cellular industry, you look at cellular 850 band. Total 850 band for whether it's uplink or downlink is about 45 meg, right? 45 meg is not much, so you lost all the resolutions. See, I have a customer call me up. See, I couldn't find my antenna because he said 45 meg frequency span, but his cable only like 20 feet, or i.e. Less than 10 meters, 5 or 6 meters, and his resolution is we actually automatic calculate resolution is about 5 feet per point. There's no way you can find the antenna. You just see a kind of a straight line. So yeah, especially for the remote radio head, now the antenna, the radio is on top of the antenna. You really, from the radio to the antenna is about 10 feet cable. You have to be really careful how you set it up, the system. We usually recommend to use the low pass mode because the cable is the broadband device, and antenna is kind of a broadband device as well. So that's the best way to make those measurements. Not use band pass mode, unless you absolutely have a filter in the middle. So that's how to manipulate distance to fault measurement. You can do manually if you need to manipulate the bandwidth, i.e. the start-stop frequency. So if you have a bigger bandwidth, i.e. broadband, then you have a better resolution. You have a better resolution. If giving the point is fixed, then you have a smaller measurement range. So you really have to play all those points and start-stop frequency. And in our instrument, typically we automate it for our customer. You just set your distance, we automatically calculate that. Okay, so we look at the measurement. We look at distance to fall. We can look at return loss, make antenna measurement. One of the key things is calibration. And there are two types of calibration. One is we call factory cal. That's the instrument have to cal every year. That's not the calibration we're talking about here. We talk about measurement calibration. In Agilent FieldFox, we have different calibration method. One we call cal ready. So the instrument turned on is already calibrated in the factory with temperature compensation. So you can literally turn it on, connect, and then make a measurement. So regardless how many experience you have, you don't have to worry about the calibration at all. And if you want to connect to a jumper cable or extend the reference plane to end of the cable, we have a method we call quick cal. FieldFox have a built-in eCal module. You can think about it as a eCal. We automatically measure the electrical length and the loss of the jumper cable, and we compensate that and give you a more accurate measurement. Also, when temperature change, we can compensate the temperature change as well. And of course, we support mechanical cal. And the nice thing about FieldFox, we use the same calibration engine like used in Agilent PNA or ENA. So the measurement results are identical to those bigger instruments. Why it's important? Because you want your lab result is matching with your field results. And it's a 4 receiver architecture, so a lot of advanced calibration techniques can be applied in FieldFox, including like TRL cals. And for 2-port measurement, same thing. Since we have 2 electronic cal kits built in on each port, so you can calibrate to extend to end of the cable, or if you just simply measure at test port, we have a cal ready, and you turn on the instrument, is ready to go. And you can set up a number of points or change frequency, will automatically handle the interpolation. In order to make the calibration really easy, we basically ask our end user, just tell us what kind of device you test. Is it 2-port or 1-port, and adapter type and connector type. We automatically choose the best cal method. Because when you're getting complicated neuralizer measurement, the key issue we see customer make a mistake again and again is choose the wrong calibration method. And we're taking care of that by FieldFox Cal Wizard. Last but not least is we in the show floor. This is actually the first time we present our instrument. This is 26.5 gig FieldFox cable antenna analyzer, spectralizer, power meter. It's all in one. And the show over here, the measurement result is consistent and similar to our PNA and PNA-X. And go ahead if you have time to take a look at the box. So in summary, cable antenna is critical for any kind of communication system. And using the right method to make a return loss as well as distance fault is critical. And Agilent have a unique contribution in calibration to make sure the measurements are repeatable and consistent with our lab. And at this time, I think here, I've run out of our time, and feel free to ask questions. Since I'm the last one, I will be standing here. Feel free to ask questions. Go ahead.
Is there a rule of thumb for a minimum percent bandwidth at which DTF becomes useful?
Okay, so question is, what's the minimum bandwidth make a DTF usable? No, this really depends on your, how the resolution you're looking at. And if, let's say, you have a very minimum, you have a small bandwidth, but you have a huge cable, and the connector you try to identify is pretty, pretty far away, then you have a very small, bandwidth. That's fine. But if you have you do a fixture type of measurement, each connector is only a few millimeters, then you need a very, very high frequency bandwidth. It's a mess. You have to play with that.
How would I know if I had enough bandwidth for my length?
Okay, in our instrument, all you need to do is tell the length of your cable, give an estimate, maybe 20% more than the actual cable, and the instrument will automatically calculate and tell you the resolution. And you can look at the resolution and see, okay, that's good or not. It's pretty, pretty obvious. Other questions? No. Okay, and we have an instrument over there, and feel free to drop by. Thank you.